MAP4C 7.3, the regular payment of an annuity. MAP4C 7.3, the regular payment of an annuity. The regular payment of an annuity was investigated in section 7.1, and what we determined was that if we continue to make regular deposits, equal amounts called an annuity, into an account, and it's earning interest over time, we can use the following formula. Now, by rearranging the variables and isolating r, starting with multiplying each side by I, because if we're dividing by I, the opposite operation is to multiply the side by I, canceling with I, and we end up with AI. Then we would want to get rid of this expression so that r is the only term on the side, and if they're multiplying, the opposite is dividing each side by that expression. So divide this side by this expression and you'll end up with 1 canceling, and we have just r. Dividing AI by that expression, we have the left-hand side. So we've isolated r, and what we'll do is switch the left and right-hand side so that it becomes a formula to help us solve for the regular payment if we know the amount of an annuity. So let's put this to practice. Investigation, retirement savings. Some financial experts suggest that saving $1 million for retirement. What monthly payment would you have to make at ages 20, 30, 40, 50, or 60 to accumulate a $1 million retirement fund at age 65? So we'll assume that the funds earns 9% per year compounded monthly. All right, so looking at this here, we have at each age, we want to know how many years are there until they retire at age 65. So you could do 65 minus their current age, and that's the difference, or the number of years until retiring. So at the beginning, at age 20, there's 45 years until retirement. At age 60, there's only 5 more years until you retire. Number of monthly payments. Now, because it's monthly, and there's 45 years in our first example, we'll do 45 times 12 and get our number of monthly payments, and this works for each. So our monthly payment, we're going to use the amount of an annuity formula solved for the regular payment for each of these examples. And make sure that you are comfortable substituting into your calculator and solving to get these values. But let's investigate more the meaning of what we can see. The regular payment for each, in order that they'll each have a $1 million retirement at age 65. But the monthly payment in each scenario differs dramatically. And we would expect this because if you start saving at age 20, there's more time in order to be able to save up money, and that is collecting interest. But we're seeing the exact effect by looking at these numbers on the right-hand side. At age 60, the monthly payments would need to be $13,000. At age 20, you would only need to make $135 as a deposit each month. So, notice for these calculations that the interest, which is compounded monthly, so we have to take our annual percentage rate, 9%, and divide it by 12 to get this value. So there's some questions we're going to address. How does the monthly payment to accumulate $1 million change as the years to retirement decrease? So we can see that as the years to retirement decrease, the monthly payment increases. So if you're running out of time to make a payment, to make a retirement fund of $1 million, you're going to need to make very large deposits, and this might be unmanageable for some people at a monthly rate. At what age do you think it becomes unrealistic to expect to save $1 million for retirement? And explain. Now, this will obviously depend on a variety of factors. This is my input. I believe that the monthly payments of $891.96 at age 40 would be too expensive for many Canadian families to afford. At this age, most families will have a mortgage and children to pay for. So, typically a mortgage is paid off in 25 years, and if you have a large expense that's regularly occurring like that, it'll be tough to save away extra money. So hopefully you begin saving up for retirement at age 20 to 30. What would you consider a comfortable retirement? What annual income do you think you will need when you retire to have a comfortable retirement? So given that I have not retired yet, I'm going to leave you this video to check out just to see some experts talk about the saving habits of typical Canadians. Next, in section 7.2, what we did was look at the present value formula. So the present value was how much needs to be invested today to be able to receive regular withdrawals. So a contrast to the amount of an annuity formula, I like to think of the 7.1 amount of an annuity formula as I am making deposits into an account that's accumulating interest starting from a very small amount, and those regular deposits continue to grow and earn interest. Where the present value formula, the present value is the amount that is in the account and is giving out withdrawals regularly. So, that being said, this kind of works like your pension, the amount that you regularly expect to receive when retiring. So, isolating our variable, we want to get r by itself, multiply each side by I, and then divide by this expression in order to get r by itself. And we can leave r isolated on the left-hand side by just switching the left and right-hand side. So we have a formula that looks similar to the previous example, and it's going to be helpful to be able to contrast the two. We'll have some example questions to help you determine which scenario each formula applies. Determining payments given the present value. Donald borrows $1,200 from an electronics store to buy a computer. He will repay the loan in equal monthly payments over 3 years, starting 1 month from now. He is charged interest at 12.5 per year compounded monthly. So how much is Donald's monthly payment? So we're going to use the guess method. Let's look at the given information. We have our present value at $1,200. Our interest rate is 12.5% per year, compounded monthly, so we divide by 12 to get the interest rate at the compounding period. And n is the number of compounding periods total, so it is for 3 years monthly is 3 times 12, 36. So substituting into this equation, and what you're going to notice here is that this is a decimal that does not terminate. It's always going to have a 666 repeated, indicated by the bar on top of the 6. So if you can figure out how to use a rational number or a fraction to represent this, this will be exact. And you can see that in this equation, I have used I as a fraction just so that I have perfect precision. There's no rounding error. So this ends up being $40.14 as a regular payment in order to be able to pay this off over 3 years. So, how much interest does Donald pay? So the present value is equal to the sum of the regular deposits, which is R, the regular deposit, times N, the number of times that you make that deposit, minus the interest. Because that interest is the incentive that allows someone to loan you that money. Rearranging this form, let's bring I over to this side. It's just I by itself. Subtract present value from this side. We end up with this equation here. And substituting in our values, our regular payment times the number of times that we made it, the total ends up being $1,445.04. The present value, $1,200, when we take our difference, we end up with $245.04. So this is the deal. $1,200 is given to you today. And if you pay it over 3 years, you'll pay the amount that you owe plus interest. And for $245.04, you can have this item, the computer, now, as long as you pay interest.